Okay, welcome everybody to my talk. Today I want to talk about some lessons we have learned when we ported our software from Windows to macOS and later to the web. 1 second, is there did anything pop up? The chat. Okay, I didn't see the chat. Okay, now I see the chat. 1 second. Yeah, lessons we've learned while porting our software. So what was the situation initially? We had been doing about 12 years of development for Windows only when we started porting our software to macOS. And in that time, we had written about 1 million lines of C++ code. And you can imagine that we had used the Windows API everywhere in our code base. Windows API calls, Windows data types, you name it. So there was quite a lot of initial cleanup to do. Our use case is a bit special because our product is an add-in, which is dynamically loaded in a host application. And that has some important implications. It means, of course, that we're not in control of the main application. And unlike developers who develop server or embedded applications, we're not in control of the computer either. That means that we have to be flexible in some important regards. For example, we always had to have a very flexible rendering engine, which needed to render into any object that the host application would give us. That could be NS views or core animation layers on macOS, or window handles or DirectX textures on Windows. And we needed a renderer that always supported DirectX on Windows and OpenGL on macOS, because that was just what we felt was best supported. That was what the host application used, etc. So we had no choice in that matter, essentially. We also share the main message, the main event loop with the host application. And we always wanted to be very quick in supporting some platform-specific features. Well, the platform-specific features the host application supported. So we could minimize the friction between using the main application and using our part of the add-in. That could mean very different things. It could mean small things. For example, on macOS, there's a triple click in a text box that selects an entire paragraph of text. Or it could mean bigger things, like, for example, our host application on macOS runs in a sandbox environment. And that, of course, means that we run in a sandbox environment as well and had to live with that. Now, when we started porting our software for the first time, really, to another operating system, of course, we were looking for some cross-platform toolkit that would just hide all the platform-specific stuff from us and would behave identically on each platform that we supported. And my talk is largely about why this does not exist and possibly why this cannot exist. First, I will talk about some problems we have encountered while porting our software and how we solve them on an abstract level, and in the second case, in a more concrete example. And then in the remainder of my talk, I will talk about some tools we have built that made cross-platform development easier and that are hopefully useful to others as well. So if you're trying to write cross-platform software, then you have your platform-independent code on one end, and you have the operating system on some end. And then the question now is, how do you design the boundary between the two? How does that interface should look like, where you hide away the platform-specific stuff? And there's no general answer to that. I think that depends very much on the semantics of your code. And I will go through a small example to see what choices we have and what choices we decided to make when we were learning how to do that stuff. So there were a couple of easy cases that I found just in our code base that have one thing in common. So one example is, for example, our rendering engine, where you have platform-independent code that renders stuff and essentially creates lists of triangles with texture coordinates. And then you have a backend that just goes over those things and issues OpenGL or DirectX commands. We do HTTP requests using the system APIs because we don't use curl, for example, because the system APIs might use the system proxy settings that the administrator has set. And there, the interface was also very easy to design. You have a function that takes maybe the URL to call and the arguments and returns data. And the last example is creating a child process and setting up some communication mechanisms. These things had very different implementation, but the interface was a very obvious design decision. What all these cases have in common is that they have very clearly defined data that goes in and data that goes out. And what happens in between isn't all that important for your application. You can hide that away in some kind of black box. But that is not always the case. It gets a little bit more complicated if you're interacting more closely with the operating system and you have to live with operating system behavior for a longer time. And one very simple example is how to rename a file. This works very differently on different operating systems. Let's look at the choices that we have on the operating systems we supported. So on Windows, there's move file X. That, of course, takes the source file name, takes the target file name, and a few flags. Some of them are even very Windows specific. I haven't even listed them here. One of them is, do you want to allow copying the file? If the source and the target are on different disks, then moving won't be possible. You have to actually copy the data. And do you want to allow overriding the target file if it already exists? By default, move file X will return an error in that case. So then on Darwin, the macOS Unix variant, and Linux, there are two functions that have very similar semantics, rename X and P and rename add to, that had two different kind of flags. And the first one is entirely unsupported on Windows. It says swap source and target atomically on supported file systems. That sounds like a very good feature. It's a strong guarantee, something that the operating system guarantees for you. Which file systems are supported? I don't know, it might depend on the Linux version, for example. And then there's a second, which is essentially the same that move file X allowed, but inverse, fail if the destination file already exists. Good. That also sounds like a good feature for me. And then last but not least, on macOS, there's another function, copy file. And that has another set of flags. It says, for example, it allows copy file ACL, lets you specify if you want to copy the access control list of your file to the target location. Well, that sounds like a useful function if your file system supports access control lists. Maybe I don't want to copy the ACL. Maybe I want to use the default ACL at the target location. So copy file lets you specify that, but the others didn't. So now you have those three different functions. How do you get a cross-platform interface that does something useful? Well, obviously, we have an answer for that. The answer is this, a function that does none of all these useful things that these functions do. Now, in fairness to the standard, I don't think the standard could do any better because that's exactly the semantics that the POSIX standard had already defined. So on POSIX systems, there's little more you can demand but this. But it's not terribly useful. All those useful guarantees, atomically swapping, don't override the target file, std file system renamed us, none of them. But we need them. So what can we do instead? Without resorting to if-defs, of course. That is ugly. We need a better interface. We need a usable interface that we can program with. And this is very hard to do on such a low level, on such a semantically low level, like renaming a file. What does renaming a file mean? What does it do? We don't know. It just says rename something. We don't know for which purpose. Because I think we don't actually need a cross-platform file rename function. And we started writing cross-platform interfaces on a different semantical level. We need other functions. We need functions, for example, to download a file to a cache in a thread-safe way. So no two processes that access the cache will ever override the same cache file or read a partially written cache file. We might need a function to create a user-specific application settings file. We might need a function to create a temporary file that will be automatically deleted for us, but which can be opened by another application in the meantime. Or we might need a function to create a document in a user-specified folder, which would mean opening the system-specific save file dialog, and on macOS, for example, creating a sandbox exception. So we need functions that have very strong semantics, and then we can implement those semantics identically, semantically equivalent on different operating systems, but often in very different ways. So let's look at a very simple example. How do we create a user-specific settings file for our application? On a Windows, there's natural location. You could put it in ThingCell app data. That already implies a choice. The choice here is that the app data system folder for application data is roaming, which means that if the user has a user profile that is stored on the server, then that user profile will be copied to each machine the user logs onto, and that will include our settings file. Good, that sounds like a good decision. We want the user to have the same settings on each computer. Then on Windows, processes can run under different integrity levels, like different privileges. If a process runs once under a high integrity level and it stores a settings file, and then it runs again under a lower integrity level for some reason, it could not read the settings it had just written. So we might decide to encode the process integrity level in the folder name. Now on macOS, there's entirely different kinds of choices we have to make. The default location for the settings might be library application support ThingCell, but it could also be that our application runs sandboxed and the settings file is shared with a group of sandboxed applications that we have written that are all part of the same application group. And then it goes in library group containers and some application group subfolder. And then there are a couple of decisions we can make just because we know what the function is supposed to do. So we might say we always want to lock the file when we're writing it with an exclusive lock, because nobody will ever want to read a partially written settings file. And we can say we always want to inherit the access control list when we're creating that file from the parent folder, because that parent folder is a system folder and probably has the correct access control list set. Now, a more complicated example is how you could create a temporary file that is automatically deleted, but which can be opened by another application in the meantime. On Windows, that's straightforward, and it's supported like that by the operating system. You can call create file. You create some file name in the system temp folder. File's readable, writable. You can create some system-specific security attributes, make it accessible by the current user only, for example. And then there's this magic flag, file flag delete on close, which says exactly what we want. It says when the last handle to that file is closed, Windows will take care and delete this file automatically for us, even if our application crashed and could not clean up after itself. That's good. Good operating system guarantee. We don't have that guarantee on macOS, so you have to do something else. Let's say we create a file. Now we create it in that application group subfolder because we're assuming that all the applications that access the SEM file are part of our sandbox. We make it readable, writable by the current user only. And there are some macOS specific things we now have to do. Maybe open can be interrupted by a signal, it will return an interrupt. We have to handle that. And then we can say, well, maybe we want to implement some manual reference counting mechanism in shared memory to clean up this file when we're done using it. Maybe that's good enough. Maybe we want to say, oof, maybe it's not robust enough. What if we crash? We don't decrement the reference count, and then we leak this temp file. So we can think about the semantics of the function, about the contract that we have to fulfill, and say, well, maybe it's better on macOS to do something else entirely. And for example, we could say, well, let's store this temporary data in a SQLite database instead. Create the same file interface for that. And then if we're crashing, we just have one file to clean up. We just have this SQLite database to clean up. And that's just a much easier problem. Clean up one file instead of cleaning up 1,000 temp files you've created. So I'm saying that cross-platform interfaces need to have very well-defined and strong semantics, and that's something that has worked very well for us. If you're introducing interfaces with very weak semantics or with too weak semantics, then you're starting to introduce, or you may introduce, subtle errors. The contract to the function is not strong enough. You don't know how that would be implemented on each operating system. And you start maybe digging into the implementation to find out. And this is a big warning sign. If you have to go through the implementation to find out what does this really do on one of the operating systems, then the semantics of your function weren't well defined. On the other hand, if you create functions with very strong semantics, like I've proposed here, then you increase the degrees of freedom for the implementers. And that's a good thing, because operating systems are very different. And when you're introducing this cross-platform boundary, where your platform-specific code starts, there are two mistakes you can make. You can start to put that at a too high level in your code, and then you miss the chance to unify some code that would actually have been identical on each operating system. This is very rare in my experience, because we as programmers are very lazy, of course. But I've done the opposite mistake quite a lot of times, and I've introduced cross-platform interfaces that were just too low level. That didn't work out that well in the end. And that always means that you force identical interfaces on very different things. It can mean that the semantics that you're imposing just don't match one of the operating systems very well. For example, a Q file, and now I believe the standard as well, has an interface, has a function Q file set permissions that lets you set file permissions. But it enforces the POSIX file permissions model on Windows, where you have read-write executable bits. And you can implement that on Windows, certainly, but it's not what Windows really does. The Windows security model is more powerful, and you don't have access to that. Or, as we've seen with a rename example, you create a function that just has lost all the expressiveness of your platform-specific functions. They supported a lot of good features. Your cross-platform version supports none of them. And that makes it a not very useful function. Now, before I go on, are there any questions? Because I can take questions anytime. If you just type them into the Q&A panel, then I can answer them right away, maybe. Otherwise, of course, we'll have more time for questions at the end. Okay, now I'll just go on for now. So you might say, okay, this has been interesting, maybe, but well, don't cross-platform toolkits like Boost or Qt solve most of these problems for us. And they are certainly very good, and they solve a lot of problems. And we use Boost, for example, but they don't always solve the problem for you. You still might encounter situations where you can actually do better than Boost or any other toolkit because you know your application and you know what semantics you need. So let's look at one example. We use shared memory a lot. Our product uses shared memory a lot to implement inter-process communication. And we use Boost Inter-Process because that offers a common API to access shared memory on Windows and POSIX systems. And now you're wondering, how much inter-process communication can you have with an add-in? Well, there are quite a lot of processes involved in our product. There is, for example, a Google extension with a little web app that we host internally that lets you import data from the Tableau.com tool into PowerPoint charts. There are helper processes that, for example, do OAuth authentication, so the user can download images from some image database into PowerPoint. There's a chart scanner that lets you uses image recognition and text recognition techniques to read essentially the data out of a chart that you might have only as a screenshot. So you have a PDF report maybe, and you want to get the data from that chart in there out and get it into Excel, into your presentation. And the chart scanner does that. And last but not least, we have a command line tool that lets you batch create presentation. If you have big reports, for example, you can update them dynamically. Things that renders them all nice for you. So that's pretty powerful. And all these tools communicate with each other using inter-process calls. Now, Boost Inter-Process offers everything you need to work within shared memory. So there is a named memory object that you can look up by name in different processes and then map it to different processes, manage shared memory. And then there's a pointer type. So you can store pointers in shared memory, actually. Because if you have, let's say, a vector that internally has 3 pointers, and it is stored in shared memory, that vector can't store raw pointers because the shared memory object will be mapped at different locations in each process. And offset pointer is a very clever solution to that problem because each offset pointer just stores an offset to its own this pointer. And this offset is the same actually in each process. And last but not least, there's, for example, inter-process named mutex to implement synchronization. Now, a little code snippet, how does that look like? Let's say you have a server process and that will create a shared memory segment with a given name. That name should be very specific, might be specific to the version of your software, to your current host, to your security identifier, because that name might live, that shared memory object might live in a global namespace. So you want that name to be specific. And then you can construct an object in that shared memory segment and start the child process, and that will look up the shared memory object and find the object. we've created. Now imagine you run those two processes, you terminate them. Now I run the server process again. What happens? Well, it will throw an error in this line and will say, oh, a shared memory object with that name already exists. And that's kind of surprising. That's especially surprising if you're coming from Windows, because on Windows, that would mean that this boost implementation does not actually use the Windows shared memory implementation. Because native Windows shared memory looks a bit like this. You can, on Windows, create an anonymous file mapping. It's a file mapping that is backed by the page file. And that guarantees that if, again, like in the temp file example, if the last process that has accessed this named memory segment, this anonymous file mapping dies, then that memory is freed for you. The page file releases the data. So if you start this again, it means you get a clean memory segment. That's good. You don't have to clean up after yourself. Good operating system guarantee. That's a feature you want, I think. But this feature is not supported on POSIX. And that has created a lot of problems in the past. So when I encountered this problem first, I started Googling for a solution. When all I found were other people having variants of the same problem for years, 10 years sometimes. So what happened? On Windows, shared memory and mutexes are reference counted, like most kernel objects I can think of. So that when the last handle to them is closed because the process has crashed, then that resource is freed. On POSIX, shared memory can be either file-backed, which means that the backing file still exists even if your process crashes, even after a reboot of the system. Or you can use the actual POSIX shared memory implementation, which seems to be limited on many operating systems. And that will still mean that the backing memory continues to exist until the system is rebooted. So POSIX here kind of assumes a server-client model where the server process would be able to clean up first any lingering memory segments before it creates a new one and creates child processes. If that's not your process model, and it wasn't our process model, then there are 1.5 solutions to this problem that I could find or think of. And neither Boost Interprocess nor Qt implements one of them. So what's the first half of a solution? There's a thing called robust mutexes, I learned. A pthread mutex, you can mark a pthread mutex as process shared, which means that you can place the mutex in shared memory. And you can mark a pthread mutex as robust. And that means that the pthread mutex will store bookkeeping data, and it will remember which process has last acquired a lock to it. So that if you try to acquire a lock, if you call pthread mutex lock, and the last owner who locked the mutex has crashed, it will return owner dead. And you know, oh, okay, my shared resource, whatever I'm guarding here, is in some undefined state. And I have to clean up or terminate or whatever is right in your situation. It's only half a solution, of course, because, well, you still have the lingering memory segment and you have to clean it up when nobody has acquired a lock to it, when nobody died holding a lock to it. There's a Boost Interprocess pull request, not by me, for someone who tried to get robust mutexes into Boost Interprocess that maybe needs some support. Seems to be a good idea. In my situation, I had to look for something else because macOS does not support robust pthread mutexes anyway. And the only resource that I could find on POSIX systems that has process lifetimes is a file log. And file logs are very weird. There are a lot of warnings about them, and they're weird semantics. And there's also a Boost Interprocess pull request by us to implement better shared memory semantics on POSIX systems. Semantics that get closer to the Windows version. So what are we doing? Something I think is pretty simple. There's some very internal method to the shared memory thing that creates the backing file. And in that memory, we do the following. We try to open the backing file or create it if it does not exist. And we try to acquire an exclusive lock when we're creating that backing file, but without blocking. So if that succeeds, then we know, this process knows it is the first one and the only one to have opened this backing file. And it just throws away the old data. And then it degrades the lock to a shared lock and goes on with its life. And if acquiring the exclusive lock initially failed, we end up here and we just wait until we get a shared lock. And so in the end, everybody has acquired a shared lock. That seems to work well in practice. There are two problems in the details, as there always are. So the first problem is that this flock call down here is not actually atomic. It first releases the exclusive lock and then acquires a shared lock. That's unfortunate, but it's not so bad, really, because there are only two things that can happen while flock has released the exclusive lock. And the worst thing that can happen is that another process comes along and acquires an exclusive lock to the same file. And then the file will be truncated twice, which seems to be harmless. The other thing that can happen is that this open call succeeds before the flock call returns, but that just inverses the order in which we acquired shared locks. Also doesn't seem to be a problem. What's more tricky is that you might have your user home directory mounted via NFS. And one of the problems with file locks is that they don't work so well with networked file systems. But all that we require here, and that seems to be required even by macOS, for example, itself, is that these file logs that we're taking here are visible locally. And that seems to be well supported on NFS. So they don't have to be visible on other machines. Now, again, there's a pull request. So we would like to get this merged into Boost in the process at some point. So here, we're also aiming for strong and identical semantics on different operating systems. And here that meant having strong guarantees by our operating system. That's always a good thing. And what Boost here did is to say, okay, they had a very powerful shared memory semantics on Windows, and they had weaker ones on POSIX, and they decided to re-implement the POSIX ones on Windows because, of course, that's easy. And wasn't actually good enough for us. We needed the more complicated version on both operating systems because that's just what we needed. So even if you have a good cross-platform toolkit, there are times where you can do better because only you know the constraints of your application and what you can live with and what you need. Before I go over some tools, are there any questions to that first part? Disagreements, comments? You can post them all the time in the Q&A panel. Do you think it would be worthwhile to put something like interprocess in the standard? Oh, whew, that's a good question. It seems I'm not sure. I'm not sure if I'm such a fan of putting so many things in the standard. I mean, it was hard enough apparently for. I don't want to avoid cases where we end up with a thing like std file system rename, where you think, okay, now we have something to interact with file systems, and that's certainly good. But the solution is only good for very simple cases. And I think that Boost interprocess is relatively complicated. It's relatively technical. Everything you do has some dependency on the platform. So I think putting it into a C++ standard that in the end has to be available or has to be compilable for anything that is, I don't know, from some embedded device to some big server machine. I'm not sure this can work. Yeah, it would need to be watered down, maybe. But how useful is it? How useful is that? I'm not sure. It also seems to be. I'm not sure how many people really use that. To be honest, that would probably be even a bigger issue. Like how useful is it really, and how many of those people are perfectly fine by Boost interprocess, or Qt. Qt also has a wrapper for that API. Okay, now I will talk about some tools, some of which we have also released on GitHub. So the first is text translation. Our software, I think, is used by 800,000 users now in all parts of the world. And at some point, we had to translate it from English to French, Arabic, German. And so, of course, now I'm talking about translation specifically. And internationalization is much more. You have to think about changing the layout of your dialogues from left to right to left, or the number formats, etc. But now I just talk about translation. And any translation tool has to have three important features. You always want to annotate the text, the translatable text in your source code, so you can easily extract it. That annotation needs to support a context that you can send to the translators so they know what you're actually talking about. And the last point is that languages are very different, and your translation tool should not make many assumptions about languages. For example, while preparing this talk, I learned that Russian has a different number of plural forms than English or German, depending on which number of things you have. And then if you have such a tool, then the general flow, if you're translating your source code or your tool, is always the same. So you have this annotated source code, you extract all the translatable texts, you send them off to the translators, and they send something back in an XML localization interchange file format, short xlif. And then you import that into your project as a resource somehow. So then at runtime, your translation tool will just look up the original text, let's say English, together with the current UI language, and return the translated string. And this is the case where supporting different native mechanisms would be horrible. You want a single kind of markup in your code. You want a single text extraction run that is at best platform independent, so you don't have to run it on each platform you support, but only on one of them. And at runtime, you want to handle strings that have the same lifetime always. You don't want a case where you have a translation tool that sometimes returns reference counted in as string pointers and at other times heap allocated basic strings. Let's keep it simple here. So Boost Locale now exists. It would do all of those things. It was added pretty recently. It didn't exist when we translated our software. So this is what it looks like. It has a translate function that also serves as the annotation. That translate function supports the context. So in the second example, I want to translate open to German in the context of opening a file and not, let's say, an internet connection. And last but not least, it supports the different numbers of plural forms in Russian, and here hopefully chooses the correct one for 3 files in the directory. And then in the background, the translate function goes to your catalog of translations and does a lookup at runtime of the English string and returns the translated one. But this is 2021. We don't have to do runtime text lookups like it's 1995. We have context-pro functions. And that's what our translation engine uses. So this is, in short, what it looks like. Let's say we have 2 supported languages, English and Russian. And then the translatable string is just an array of those 2 versions, the English and the Russian one. And the translate function, of course, will pick the right one, depending on our UI language. And then we have a macro, unfortunately, that does the magic, returns the correct translatable string, given the string and the context. And if you have that, then you can put it all together and here print cancel as in Windows dialogues on the command line. So what does a translookup function look like, or the macro? Well, it looks like this. So the translookup macro calculates a hash at compile time of the string that you want translated and the translation context. It calculates a murmur hash specifically and uses the murmur hash as a compile time lookup key in a map. And that translatable string map here then contains a member with the right translated text. So here you see the hash would usually be a 128-bit integer type. There's no built-in 128-bit integer, so we split it into 2 64-bit integers and use these as the compile time lookup keys into our map. And now from looking at that, you can probably guess what the output of our build tool is, the translation build tool. Well, it outputs template specializations, of course. It processes the xlib files we get back from our translators. It looks at all the text. It calculates the same hash, but during the build time in some script. And then it outputs CPP files that are filled with such statements. And we link them, and then the translation lookup is at compile time. And that has one big advantage, and especially in a cross-platform context. I don't have to think about that moment when our text translation engine reads some file on the disk. For me, this gives me, I'm not sleeping well, let's say. There are so many things that can go wrong if you are running, especially if you're running as a desktop application in the business sector where you have system administrators. You have users deleting files. This is just a support nightmare. So if I can avoid this and just link in my resource at compile time where nothing can go wrong, then I sleep well. So just a short reminder what const_expr functions can do, because they are very powerful now. So one big limitation is that they must accept and return only literal types. And literal types are scalars and references, aggregate types that you can initialize with brace initialization, for example, an array. And it can be types with const_expr constructors and destructors, as long as all base classes and data members are literal types themselves, and all arrays of such types. And then, most importantly, const_expr functions can contain if and switch control statements, loop statements, and even local variables, as long as these are initialized and literal type. That makes them very powerful and easily powerful enough to implement the hash function. I think it was just a matter of taking the code from GitHub and then making it a const_expr function. So this is just the wrapper around it. And you can see it's a template function. The template implementation even takes a pointer to the beginning of the character array, and even that is supported in the const_expr context. So that was pretty straightforward to do, actually. And here, again, we were aiming for strong and identical cross-platform semantics, and that includes the build process. That includes the external tools we need to build our software. You want them to run on all your platforms as well and have similar semantics on all of your platforms. The least different tools you have to support, the better. Now, to the question, Jeff, is there a reason for the macro? I don't know. I didn't check. It was a macro, and sometimes one reason why we do it has to do with the error reporting. I come to that in a moment. Sometimes we prefer macros because our error reporting sometimes sends the code location, the source location where an error occurred. So that's one reason. I'm not sure if that's the right reason here. I would have to check. I don't know, actually. It could be that we can make it into a const_expr function. If that's the only question, then I just keep going. Regarding error reporting, we have a very powerful and pretty special error reporting approach and architecture that I think we've done entire talks on. We use a lot of asserts in our code, and we leave them in, even in release builds. And we always check return codes from system API calls, all of them. And for each system call, we distinguish between expected return values and unexpected return values. So if you are creating or opening a file, then it's always an expected case that that file does not exist or the location does not exist. So that's something you always have to handle practically. But it would be very surprising if the create file call suddenly returned error out of paper. So I'm not going to write code to handle that now. It's probably never going to happen, but it might. So our error reporting architecture checks for unexpected return values and then sends an error report. And that error report is sent to our backend servers, which analyzes that error report. And it might check if we have fixed that error. Have we seen that before? Have we fixed it? In which build of our software have we fixed that problem? Or do we need more information from the user to diagnose the issue? And then our backend reports back to the process that encountered the error. And the process might then decide to download the update, install it silently, or even reload it silently, so the user will never encounter the problem again. Or it might, at the very least, display a more helpful error message to the user that says something like, "You've encountered an error that we're looking for, please contact our support." On the developer end, we have a little database application, and we can look at the error reports that came in for different versions of our software, different operating systems. And the backend groups them by the source location where they occurred. It even analyzes the stack and checks what's the last most relevant stack location and displays that. So that's an extremely useful tool. It finds a lot of bugs that depend on the user's setup, that depends on the system administrator sometimes. Does the user have crazy security software installed that we've never seen? Things like that. Now on Windows, the core of this functionality is minidump write dump, which is an extremely useful function that writes, as it says, a dump that at the least includes the stack and the registers. And that's something you can load in your debugger. Microsoft provides symbol servers for all system libraries, and the Visual Studio debugger can then symbolicate the dump, and you see the stack trace and even local variables sometimes. And that's a lot of information in maybe 100 kilobytes of data. Extremely useful. And nothing similar existed on macOS, and I think nothing really similar exists on Linux. There is the Google Breakpad Crashpad project, of course, that is pretty popular, but that made a couple of strange decisions, which is why we didn't want to use it. So for example, probably the strangest decision is that it writes Windows minidumps manually on all supported platforms, which is probably a file format that is at best kind of documented. And then, of course, to open a Windows minidump for a macOS dump, you have to write your own analysis tools as well. Visual Studio won't help you. So that was just a lot of custom code that now we would have needed to support for a not so powerful solution. And there was a better solution, at least for macOS, because the binary file format for macOS is very well documented. And that includes the file format for core files. It's a little bit different on Linux because for the ELF file format, I checked that I think the core file format is not actually standardized. You have to check what GDB does and what GDB requires. But all that we had to do was to write a valid Macho core file that only contains stack memory, and then LLDB could just read it and open it without any further ado. So, two small slides how that looks like. macOS is has a bit special kernel where you have a lot of message sending between different processes. You can look up a message port by name, and then you can send a process a message. And in that case, we have to send one message. If the process is crashing, the first thing you want to do is set up another process that actually does the error reporting. And that is in a clean state. If your process has encountered an error, you don't know if that can do that many useful things. So what you can do on macOS, even if you're a sandboxed application, is you can send access rights to your process, to the crash handling process, by sending a message to a port that you've looked up. Okay, and what you have to do then in the crashing process is pretty simple. You go through the Macho core file format into the system functions, and you assemble the necessary information. You acquire a list of all the threads. You get the registers for all those threads. You get the memory regions. There's a function machvm region recurse that goes over all memory regions. It will even tell you, is that a stack memory region or not? And then you include it into your binary file. And if you've assembled all that information, then you write it into a file. The binary header, the thread states, the memory segments, and the actual memory contents from your stacks. And the resulting file can be loaded into LLDB as a core file and zipped. It is like 100, 200 kilobyte in size, similar size to Windows minidumps. It still needs some additional metadata that we send along. You need to send along information about all the shared libraries that were mapped into your process. And we do that. Which shared libraries were mapped at which start address. And then our backend can analyze that just like it can analyze macOS, Windows mini dumps. So you need the debug symbols for your own builds, of course. We cache all the system binaries for macOS because unfortunately Apple does not provide symbol servers like Microsoft does. And then we have a little wrapper around LLDB that loads our core file, loads the core file with the custom meta information we send along, and then looks up the macOS binary with the correct version and loads them in LDB at the correct load address. And then you get a valid stack that you can analyze programmatically, even using the LDB APIs. Very, very nice. It's been very useful for us. It finds a lot of bugs. And we have open sourced this in a way that doesn't run the way we've published it, but the interesting parts are there. I think there's maybe an XML parser that is missing and writing zip files is missing or something like that. But the top parts I talked about, they're all there. Now, last but not least, I've said that in my headline that we've also moved ported parts of our code to the web. So I said that we ship with a little Chrome extension and a web app that gets hosted internally by our application that lets the user import data from tableau.com. So when we started writing this little web application, we asked ourselves, what language do we want to use? And it was pretty clear that JavaScript is a hard no, but TypeScript looked much better. It was type safe. It had these awesome, well, it still has, these awesome type definition libraries that provide type descriptions for legacy JavaScript implemented, for JavaScript libraries. So you can use any JavaScript library in a type-safe way because there's a type description of their interface. But sharing code with C++ was impossible from TypeScript, sorry. And there's always just a little bit of code you want to share. Maybe just a data structure. Maybe you're sending messages from your web application to your native application. And at least that data structure you want to share. But there was no way to do that elegantly. So we thought, well, maybe we should look into MScript. Maybe that's the better way. Maybe we should just write web applications in C++. That's what we know best, where we have a big algorithm library. We have a very powerful code base. But then we found out, well, now interfacing with JavaScript loses type safety again. Because in MScript, there are no wrappers for the standard DOM APIs, for example, let alone custom JavaScript libraries, for example, the tableau.com JavaScript library. So from MScript, the way you're interacting with raw JavaScript is a bit like in this example down here. It's a lot of type unsafe calls. It's a type unsafe lookup for a global XML HTTP request object, a type unsafe call to its constructor. We're just assuming it doesn't take any arguments. We're calling an open method we hope exists and pass it some number of parameters that we hope is correct. So this was not great. And then we thought, well, maybe we can combine the best parts of those two approaches, of the second TypeScript approach and the MScript approach. And we decided to build a little compiler that takes those type definition libraries. So this is an example how they look for the document DOM element. And you see the properties or parts of its properties. They are described. What type do they have? URL is a string, cannot be null, apparently. It's read-only. The active element can be null, but it's also read-only. And then there's a title, which is a string, and it can be written and read. And there are type definition libraries in this GitHub, definitely type repository that's now included in TypeScript. And there are such description for over 7,000 JavaScript libraries. It's an extremely powerful tool. And we knew, well, we don't even have to write a parser for that thing because TypeScript already comes with a very powerful TypeScript parser. This is a TypeScript snippet that takes a file name, it creates a TypeScript program. That means it parses the TypeScript file, including all the dependencies. And then you get the syntax tree for that TypeScript file. You can get back a reference to that source file and iterate over all syntax nodes in that source file and check, is that node a function declaration? If it is a function declaration, what's the name of the function? What's the return type of that function, its arguments, etc. So this was a very powerful parser that now we only had to write the tool that creates a valid C++ from that. And that's exactly what we did. It's called TypeScript. It's published on GitHub. And it's a tool that compiles TypeScript interface declarations to C++ interfaces. So you can make type-safe and idiomatic calls to JavaScript libraries from Mscript. So if the JavaScript code would be as simple as assigning a string to the document's title, then the C++ version looks kind of similar, at least. You call the document function that gives you a reference to the document, and then you call its title setter. We don't generate a different name for the setter at the moment. And that setter function takes only one kind of argument, the JavaScript string. So there's no way you can do a type error here. Now you can imagine writing this tool has been a lot of fun. If you're writing on a product, working on a product for 15 years, when you get a chance to write something like on a clean slate, that's already quite a lot of fun. But there were quite a lot of challenges. Before I come to the challenges, this is what the generated header looks like in a way, in a simplified way. So all the interfaces that we generate, at its base, there's some JavaScript object, JS object here, which contains an Mscript value. An Mscript value is like a reference to an object in the JavaScript world that is reference counted in the JavaScript world. So we can make those same type unsafe calls on that. We just wrap them in a better interface. And here, the document interface, you see it has an accessor for the URL, for the active element, and it has a getter and setter for the title, because that's not a read-only property. And then the implementation for document title wraps those type unsafe calls that we don't want to write by hand because they're ugly and error-prone, and wraps them in an interface that guarantees correctness. And we can use that to write TypeScript in itself. So TypeScript in itself is almost self-hosting at the moment. That means it can compile the interface definition for the TypeScript compiler itself. So the TypeScript code snippet I've shown you before in C++ looks like this. Again, I'm creating an array with a TypeScript file name. I create a TypeScript program from that, which instantiates the TypeScript parser. And then I can iterate over all syntax node in that TypeScript file. And you see here this for each function, which is a TypeScript function, gets passed a C++ lambda as a callback. So the TypeScript implementation will call back into C++, into our lambda, where we can then check, is that syntax node a function declaration or a variable or a class definition or what? Okay, so we're using that and it's working pretty well. There are a couple of features that are still missing that I'll come to in the end. There are a couple of interesting language differences that made developing this tool challenging, as you can imagine. One of the simpler ones is that in TypeScript, the declaration order does not matter. So this is valid TypeScript. In the first line, I define a union foo bar, which is the union of type foo and type bar, before I've actually declared foo and bar. So we can't translate that literally in the order in that we find that. We do something pretty simple. We collect a list of all the types in our file and then generate a lot of forward declarations, for example. And I think in the end, sort files according to their dependency. So we make sure we have issued all the type declarations before for foo and bar before we issue the union declaration for type foo bar in C++. TypeScript also supports enumerations with string values. The enumerations can even have mixed string and integer values. What do we do in C++? Well, we just declare a normal C++ enumeration class with just the enumeration values. And we implement custom marshalling. So we implement custom marshalling and send something else to JavaScript. So here there's a structure, marshal enum, that our tool can look up at compile time, and that contains a function with a map that maps the C++ enum value to the JavaScript string value that we actually have to send to the JavaScript world. And the most interesting challenge has been how to implement function callbacks. So the first line is what you want. In JavaScript, you set the onClick handler on the document, and you pass some function object to that onClick handler function. And that JavaScript function object will be stored by the document in some member, probably. It's going to be reference counted, like everything in JavaScript is. Now, of course, you can't just pass some C++ function pointer to the JavaScript world and store that in JavaScript. That won't work. You have to have quite a lot of glue code. So in C++, this would look like the following example. Again, there's some macro to hide a small contraption here. But it looks like we're declaring a member function on click that takes a mouse event as an argument. And that's the onClick handler we want to set. So when the user clicks with the mouse on the document, then we set the document title. Okay, pretty straightforward. Now, what's the contraption that the JS member function macro has to hide? That's quite a lot, actually. So what do we have to do? Instead of generating a member function, we generate an object, which is a JavaScript function on click. And that JavaScript function object gets a function pointer, a C++ function pointer, and a this pointer. And it sends those two things, those two pointers, it sends them to the JavaScript world. It calls into JavaScript, and it will create a JavaScript function object, which just captures those two values, a function pointer and a this pointer. And that JavaScript function object is then returned to the C++ world and stored there as this mscripten reference, mscripten value. Now, when the user clicks on the document and the click handler is called, this JavaScript function object will be called. It will unpack its members, function pointer and this pointer, and it will call back into the C++ world. And it will call function call, a generic function that takes a function pointer. And that function will know how to cast the function pointer back to the correct C++ signature, and we'll call it. And then we end up in onClick wrapper again. And that will do the last step. All this code is generated for you, essentially. That will do the last step. It will cast the this pointer. It will look up, it will call the correct member function on this pointer. And it will even unwrap the arguments, because all the arguments are passed in an array like JavaScript does. So it will unwrap the correct number of arguments. And then in the end, our member function onClick impl is called with the right member function. So that's quite a lot of stuff to implement callbacks, C++ callbacks in JavaScript. And the other thing that is hidden here is that this JavaScript object up here is kind of a Rai wrapper for our function. If that thing is destroyed, but our JavaScript object, our JavaScript function object still lives on because it's reference counted, then it will deregister the C++ callback in the JavaScript world. It will essentially call its function object and say, I'm gone. If you are still called for some reason, then don't call me. My function pointer is now useless. Okay, so that was one of the harder features to implement. What challenges do remain, and which is why we've made it open source and hope that it is useful to others. Well, the first and important feature is that TypeScript supports generics, which are a lot like C++ templates, for example, for collections of things. And we want to support that. That's one of the first features on the list, probably using C++ templates. And then there's a very interesting feature, which is called indexed access types. So if you've programmed in JavaScript, you probably know that some functions, especially those event listeners, have a very peculiar interface. You call add event listener, and the first argument is a string, which says which event do you want to register. That string can be click, for example, or key down. Now, the TypeScript authors had to wonder, okay, how do we make this into a type-safe interface? And they had a great idea. Now, add event listener in TypeScript is a generic function, and its template argument is a type K, which extends key of document map, which means, well, it can be one of the keys of document event map. It can be the click string, or it can be the key downstream. Okay, now we've expressed the valid list of strings we can pass. And then they had another good idea and say, okay, the event type of our callback is also different. So we use the document event map as well to look up the correct type of the event that will be passed to our event handler. Okay, so this is a bit harder to express in C++ maybe. And what we thought about was maybe generating from this document event map, maybe generating overloads for add event listener with tags, for example. So you would call add event listener click tag or something like that to make this close to the way you would write it in TypeScript, but still also idiomatic C++. And last but not least, we will still work on better performance, because the way we are currently issuing calls to JavaScript by passing those strings, calling a function by string, accessing members by string, this is very, very slow, because we're always sending a C string to the JavaScript world. And in the JavaScript world, that C string has to be unpacked from this WebAssembly memory array and transformed in a JavaScript string to then look up the correct property or function to call. This is, of course, pretty small. We might do something like generating JavaScript functions that can be statically linked or something that's supported. Okay, so this is the last part of my talk. The GitHub address again, and then I would be open for more questions. And I thank you for your attention and for having me.